2011, when the Atacama large millimeter submillimeter array first issued a call for proposals, they got so many proposals that only 1 out of 8 proposals got observing time. So why were astronomers so crazy about ALMA? Because they knew that ALMA would be the most powerful telescope on the ground. So today we are extremely honored that the director of ALMA Observatory, Dr. Pierre Cox, is here to tell us all about ALMA. But first, the director of ASIAA, Professor Chu, will introduce him.
Good afternoon. I'm going to introduce, so we all know that ALMA, Atacama large millimeter submillimeter array, is the largest, the baddest telescope, with the highest resolution and everything. It's the ultimate telescope we all want to use. And the director of ALMA now is Dr. Pierre Cox. And if you search on the web, you can find very little information about him. And I happen to be working on a similar kind of field as he did, so I know his scientific background. So he did a lot of work on the, it's mostly dust and molecular emission from different kind of objects. So he started with like a star-forming regions and evolved stars and plankton nebulae. Then he moved on to the hot topic, high redshift object. And from there, then it's just like he accumulated lots of citation count. He has like over 200 papers and with over 10,000 citation counts. And he's very well known scientifically in the area of millimeter and infrared observations. So he did a lot of ISO observations as the former days for infrared, mid-infrared observations. And he was the former director of the IRAM. IRAM is Institute of Radio Astronomy Millimeter. I translated into English. It was a French word which I cannot pronounce. So from there, then he was recruited and then became the director of ALMA. Now he's going to tell us everything about what ALMA can do and why it's the largest and baddest telescope on Earth. Here, Professor.
Is working?
Maybe higher.
Is this working?
Yeah. No, not too well.
I should. It's a lot of noise. Yeah, I'm going to use this. This is working. So good afternoon, and thanks for your kind words of introduction. I discovered that we worked on the same sort of type of objects, and we are sure that we met somewhere, but we are both forgetting where it was, I think. It's a long time ago. First of all, I'm very pleased, and it's an honor to be here in Taipei and to give a presentation about ALMA. I know that in Taiwan there is a very vivid and active and interested community working for ALMA and using ALMA very efficiently. So it's a real honor to meet you and to be able to discuss about the current situation of ALMA. So in my talk, I would like to provide you an overview of where we are with ALMA, what ALMA is, for those of you who don't know that. Present you also scientific results and then the future, and that will then be the end of my talk. So just as a reminder, ALMA is an array of 66 antennas that is working and using the aperture synthesis technique and operating as a zoom array and covering the entire wavelength range from the lowest frequencies and the millimeter wavelength range up to the high frequencies up to 1 terahertz or so. It is located in the northern part of Chile, and I will comment upon that later on. And here's everything. It is remotely operated from a site, which is the Operation Support Facility, which is located at 3,000 meters, whereas all the antennas are located at 5,000 meters on the plateau of Chastan Tor. The array is movable and can go from a very compact configuration with a distance between the antennas of about 300 meters to a very extended configurations where the antennas can be displaced up to 16 kilometers, so roughly the surface of Taipei. And it's built to operate for 30 years. So ALMA is operating in the millimeter, submillimeter wavelength range, and very briefly, that wavelength range is essential for astronomy because it is the wavelength range in which you can probe the cold universe. Essentially, all the regions where the stars are formed, so you can both measure the dust continuum, but also because the techniques you're using, you can sample the light in such a way that you can identify the species of which the gas is composed of, and it identify the molecules of the interstellar gas. And the millimeter regime is a key regime to do astrochemistry. So it's a movable feast because what you're doing by moving the antennas is to mimic an antenna which has a size which corresponds to the biggest distance between the antennas. So if you have a compact configuration of 300 meters, it mimics a 300-meter dish. And if you have up to 16 kilometers, it mimics a 16-kilometer diameter dish. So of course, building such a thing is impossible. So what you do is populate with individual antennas. And what you then do is to use the Earth's rotation during an observation, during which, of course, the position of the source doesn't change, but the relative positions of the antennas with respect to the source are changing, and hence you recover the information to retrieve the image of the source that you're observing. So essentially, you use the Earth's rotation to do an image of the source. So this is the plateau de Chastan Tor at about more than 10 years ago, when there was no antenna at all, and when the project was discussed in the different regions. And about 10 years later, this is an aerial view taken from a plane, where you see the beautiful landscape of Chile, and also the telescopes here, the antennas which are in the center array, and all this is at 5,000 meters. You also see the roads and the different paths that allow you to change the positions of the antennas. This is a view from at night, and as you can see, although it's a very clear sky, it's always very cloudy because there are at least the two imaginary clouds there, which are here and there at the bottom. So ALMA is a global project which has 22 countries which are part of it. There are the three main regions: East Asia with Japan, Taiwan, and the Republic of Korea since last year. North America with the United States and Canada, and Europe through the European Thousand Organization with all that suite of countries, and of course Chile as the host country. This is a picture I took about 10 days ago when there was a visit of the ESO Council, and you may notice at the back here the Taiwanese flag. So why Chile? This is a map of Chile is here in South America, so it's really the antipodes. This is a map, an old Japanese map, by the way, from the 18th century. And the reason why Chile was chosen with respect to other possible places is very well illustrated in this particular map, which shows about 30 years worth of data obtained by a satellite to study the water content of the Earth and the coverage of the atmosphere, in particular the cloud coverage. And so as you can see, there are a few spots on Earth where there's nearly no clouds at all over 30 years, and one of them is the Antarctica, and the other one is Chile. Now, for logistical reasons, the Antarctica is very difficult, and Chile is the chosen place for doing astronomy. The reason is that you have the Humboldt Current from the South Pole, and then you have the barriers of the Andes, which creates a channel of very good dry weather, and so excellent to do astronomy. The other reason that ALMA is where it is that you wanted to extend the antennas over a large array, and there are not many places on Earth where you have a plateau which extends over many kilometers, and the one in the Atacama Desert is one of the very few. So this is, again, what I just showed, and this is the other, another picture of ALMA. So what is the mission statement of ALMA? It is to collect and deliver high-quality data sets to the scientific community by operating, maintaining, and further developing the state-of-the-art observatory to observe the universe at a millimeter to submillimeter wavelength range. And to that effect, ALMA will provide a stable operating interferometer, maximize the availability of the array, and make the operations user-friendly to facilitate science by the broad community. So that's very easy to say. It's very difficult to do it. So the fundamental goals of ALMA operations is essentially to facilitate the scientifically efficient use of the joint observatory and consistent with operating safely at high altitude. And the other thing is that the operations mode will be developed and implemented so that it allows the antennas, the instruments, the data flow, and the infrastructure to work together in a fully coordinated fashion and to adapt very quickly to changing atmospheric conditions. So why is ALMA a very special observatory? So as I say, people are living and working at 3,000 meters, which is normally the altitude where the observatories are built, and the antennas are at 5,000 meters. Now 5,000 meters is a place where your brain works about half the time, half its capacity, and it's very physically very, very complicated. So there's a lot of issues with ALMA, which makes it a very, very special observatory. When something is happening at the antennas, then you have to go over 40 kilometers of road to reach the antennas. The other thing is that the site, although it's a fantastic site, has two winters, the normal winter, but also the so-called altiplanic winter, where it can also rain. That happens in February, in the summer. So in the February, we don't observe at all, we do maintenance. And then there are hazards, and one of them is a volcano nearby, the Lascar volcano. So that was taken about 15 years ago, but it can happen again. So one thing is that I have been explained by the Minister of the Mining in Chile, that whenever that happens, everything flows and flies to Argentina, and Chasnantar Plateau remains intact. There are also earthquakes, of course. So the governance of ALMA, I just show you that to give you a flavor of the complexity of the organization. There are three parties: funding agency, which is in East Asia, Europe, and North America, was the National Institute for National Sciences in Japan, ESO in Europe, and the National Science Foundation in North America. And then you have the executives in Japan, which is the National Astronomical Observatory in Japan, ESO, and the National Radio Astronomical Observatory in North America was AUI, which is Associated University Incorporated. All that is ruled by agreements, a trilateral agreement and a trilateral management agreement. And then underneath that, you have the ALMA support centers. One of them is being here in Taiwan, both in East Asia, in Europe, and in North America. And all that is then governed by the ALMA board, by myself, the ALMA director, and then the JAO. So what is the status of ALMA? So ALMA has been constructed over 10 years, and the construction is efficiently finished last year in September 2014. There's still a number of remaining little things from construction that have to be done. And one of the biggest one is the construction of a hotel where people can live decently, which is being built today and will be finished next year. So for those of you who will visit next year in the second half, you'll have a decent place where to eat and where to meet people. All the 66 antennas are available and currently at the high site, and we use roughly on average 47 antennas with a minimum of 44 and a maximum of 54. The compact array, which is also called the Morita Sun array, which is an ensemble of 12 7-meter antennas and 4 12-meter antennas for total power observations, has been accepted and is now used for scientific observations. And finally, the long baselines have been all tested last year, very successfully so, and as a result could be offered to the community for observations this year. So that's the view of the forthcoming residence, which will be built and which is the biggest remaining part of construction. The status of the receivers is as follows. All the antennas are now equipped with exception for band 10 for about 5 or 6 antennas, with 7 receivers covering the wavelength range from 3 millimeters down to 350 microns, corresponding in frequency from 84 to 950 gigahertz. All those are offered for the current observing cycle, together with the long baselines offered up to 10 kilometers. So this is a real milestone in terms of achievement, and as you can see, ALMA is very close to achieving the original goal of having all the windows accessible from the ground in the millimeter, submillimeter range available for observations by the community. There are a few exceptions. There are 3 receivers and so 3 frequency ranges which are still not covered. It's the range from 163 to 211 gigahertz. It's the band 5 that is being constructed as we speak by Europe. And then the band 2, which is something which is being studied in North America and in Europe. And also the band 1, where Taiwan plays a very important role. I will comment on that later on. So as was mentioned before, indeed in September 2011, the first cycle of observing time called early observations started, and there were 900, nearly 1,000 proposals submitted for only 500 hours of observing time, with only 16 12-meter antennas, 4 receivers, and with only the longest baselines of 400 meters. So all the data of that cycle have been delivered, and many of the papers published are based on these things. That was followed by cycle 1, which started in January 2013 and ended in May 2014. There were a bit more than 1,000 proposals submitted, 1,100 proposals for 800 hours, with 32 antennas, the compact array, the same receivers, a bit more in baseline of 1 kilometer, and the data are being delivered and is in progress. Note that for these cycles, the time is more than a year, simply because the observations were done while the facility was still being under construction. In cycle 2, that started in last year in June and ended, in fact, at the end of September of this year. For that cycle, like 1,400 proposals were received for a total of 2,000 hours, and we offered 34 12-meter antennas at least. In fact, during the whole cycle, we had more than 34 antennas at all time, together with a compact array, a suite of receivers which included, in addition to the baseline receivers, the receivers at band 8 and 9, and then the longest baseline for only 1.5 kilometers. So that is now successfully ended together with the carryover of cycle 1. So this is an interesting graph which shows the whole evolution of both the observing efficiency since the beginning of the observations in cycle 0 and the number of 12-meter baseline antennas used for science. So first of all, you see that there is a gentle increase in the number of baseline antennas, going from about 15 at the beginning and ending at the end of cycle 4 on average at a number which is about 43 or so. The decrease here is not artificial. It is simply because at the end of the cycle, we started to move the antennas for the long baselines. In terms of efficiency, there is an equivalent increase in efficiency here, with efficiency about 80% or so at the end of cycle 2. And that is really what we would like to have in the full operations and stable operations of ALMA. So this is a cycle 2 in more detail, which is interesting for those who are using ALMA. Simply, the thing that I would like to show here is again the increase even in cycle 2 of the number of antennas which are used. And this is a thing which is again easy to say, very difficult to do, because it depends on the maintenance and a huge amount of work, both by the software, the computer, and more importantly by the engineering. This is again a plot showing the number of antennas, both 12-meter and the compact array. So you see that we reached about something like 58 antennas in total at the end of cycle 2. The completion rate is also increasing, and so this is more detailed. But important number here is that the execution time is about 80% at the end of cycle 2, which was a very good number, which was a number which was predicted. So what will ALMA and what is ALMA doing? As was said in the introductory remark, ALMA is the best, biggest, greatest, most fantastic observatory in the world, so essentially it can do everything from the study of the galaxies in the early universe down to the formation of planets around stars and the chemistry of clouds and new solar systems. So I'll show you a few, what I think, very nice results of ALMA. It's biased because there are so many results that it's very difficult to choose. The output of ALMA, first of all, is growing, and at the end of September, there were about 285 published papers in refereed journals. And what is interesting to note is that the biggest share is from cycle 0 data. And what is interesting is that about more than 70 papers are based on data which result from science and verification work done at the observatory by the JAO staff and then released publicly for use by the community. And indeed, these data are very much used, and I think that's a good thing. The other thing which is noteworthy here is that about 8 to 7% of all the papers published on ALMA data are published in Nature and Science, which I think is a very high number, which remains constant over the cycles. The distribution of ALMA papers by region is also interesting. You see that the share is quite well respected, with ESO in North America having about 40% and East Asia like 17%. What is interesting though is that the use of science verification data is there's not much use here in East Asia and Taiwan or elsewhere. So this is a plea for you to use the science verification data because I think they're very, very interesting. So a bit of ALMA science. I will first start from the solar system and then go to the high Z galaxies. This is the first example of the very successful long baseline campaign at the end of last year. It shows the results on the continuum of an asteroid called Juno, which is orbiting between Mars and Jupiter, at a band frequency corresponding at 230 gigahertz. Those are 5 consecutive executions over 4 hours and showing the rotation of the asteroid here. The beam size is 0.04 arc seconds times 0.03, which corresponds at the distance of the asteroid to a physical size of about 40 kilometers or so. So I think that is pretty impressive, and it's certainly much better than the Hubble Space Telescope. Another nice example of the solar system are measurements which were done on the Pluto-Charon couple, and the reason for these measurements was that the mission New Horizon that successfully flew by this Pluto and its system of moons asked me about 2 years ago if they could use ALMA to define more precisely the position of Pluto to make their mission the most efficient possible. To my astonishment, the position wasn't very well known, and so we improved that by measurements and had an astrometrical position of 4 micro arc seconds. And I think that's pretty impressive, and that saved the mission, and this is another view of taken by the New Horizon mission. Examples of ALMA science, the 2 big cornerstones of ALMA science are the study of protoplanetary disks, so matter around young stars forming planets and understanding the chemistry of these disks, and then of course the galaxies in the early universe and trying to understand what their distribution, composition, and morphology is. So the long baseline campaign of ALMA produced 2 beautiful results. The first one is this image that everybody has seen, which is HL Tau, and which shows beautifully, and it was a big surprise in fact, how this system has a series of very dark gaps here, which are supposed to be the result of planets being formed. And the other result is here, which is an Einstein ring of a lensed galaxy at a redshift of 3 or so. And I will comment on this later on. So let me first start with the disks. There has been a lot of very interesting work done on protoplanetary disks. And here are a few examples of studies where you see Keplerian rotation in this disk the effect of winds in the disk in this example, and also the chemistry where inside the disk, in fact, it is so cold that the molecular gas in the CO freezes on the dust grains. And to really probe the interior of the protoplanetary disk, you have to go to other molecules like N2H plus here to see the inner structure of the disk. This chemistry, the stratification of the chemistry is typical of protoplanetary disks. And this is a very nice example where you see in this particular system, IM looping, a double ring in the species DCO+, which is a result of the freezing of CO in the mid-plane here and in the outer disk, and creating these sort of chemical effects where you see a double disk in this system. Evolved stars is, I think, another very important topic for ALMA. There have been a few examples, and I'm looking forward to further observations of these very interesting objects. As was said before, indeed, I did work in that subject before. But as you can see, this is a result of an early observation in cycle 0, where you see a very intriguing spiral structure, which is due to the fact that there are two stars orbiting around each other. It's a binary star, and so producing that sort of spiraling ejection of matter in the interstellar medium. This is another example of the red rectangle, where you see a rotating equatorial disk and a low velocity outflow that occupies more or less this X-shaped form. I think what is interesting in evolved stars is, apart of the chemistry and the dynamics, is to understand the formation of dust grains. And I'm pretty sure that with ALMA, with the high angular resolution and the sensitivity, you can really probe the interior parts around the star where the conditions are such that dust can form. And that process is a very important process which is still poorly understood and certainly not very well constrained by observations. So those were stars of about a few solar masses. Since I mentioned dust formation, another very important topic is the issue of understanding what the yield is of dust formation in very massive stars that explode as supernova remnants. And this is a very nice example of dust detection in the close-by supernova remnant 1987A in large band dynamic clouds, where you see here the Hubble Space Telescope image of this. And in the middle, in red, is the emission in continuum that ALMA detected from the dust grains. What is interesting is that the mass of dust grains estimated by the authors here is about 1/4 of a solar mass. And that amount of dust was created over the last 30 years since the supernova explosion. To my knowledge, this is the first direct measurement of the dust yield in a supernova explosion. Of course, the question is if that survives the retro shock of the supernova or not. But it's very important because it bears the fundamental question about how you form dust in the high redshift galaxies at redshift of 5 or above, where we know there's copious amount of dust, but not enough time to form the dust for the more normal AGB stars that take a long, long time to form the dust. So you have to do it for supernova explosion. Let's go to nearby galaxies. This is an example of a measurement, direct measurement of the mass of a black hole by Onishi et al., where they measured in HCO plus and HCN the gas around the black hole, and through the cinematics and the dynamic of this gas, estimated that the black hole has a mass of 140 million solar masses. Let me now go to the high Z and show you a few examples of gravitationally amplified sources. This is the first example that is based on a survey done in the South Pole Telescope, where they found a series of very strong 2 millimeter sources in their survey, and those were very good candidates for amplified galaxies. Now, once you have these measurements, it's very difficult to know what the structure is with the South Pole Telescope, but also it's impossible to define the distance, or very difficult. With ALMA, it's really very easy to do that, and ALMA is a fantastic machine to not only image high Z galaxy, but also to directly measure their distance. So these are images superposed on the Hubble Space Telescope of a series of these sources, where you see in red the continuum emission of the sources, and you see arcs and dots and so on and so forth, which provides you